For several years now, here at the Congress and at the camp, we see that we have a GSM network, that we operate our own network, that we have some services like recently GPRS or roaming between the different parts of the areas in the camp. All of this started around 7 years from now with a talk at the 25C3. And a bunch of projects emerged from that over the years. But wait, there's more. Right now, the people running these services and running these projects are starting to play around with 3G. And for everybody who doesn't know what 3G is, like I did for like 5 minutes ago, 3G means that we will have HDSPA and data services on our GSM networks. And I'm very honored to introduce to you this evening Harald Welte, a member of our chaos family for several years now, known maybe from the kernel development. I first read his name while debugging a chip card driver that stated all bugs introduced by this guy over there. So other people may know him from gplviolations.org, where they try to enforce the GPL. So please welcome Harald Welte, and stage is yours.
Hi, welcome everyone to this talk about running your own GSM network or running your own 3G network rather, sorry for that. And in more technical terms, the slide titles with lots of acronyms as it is customary in the telecom world. So forgive me if there's too many acronyms, but I didn't invent them. I just try to use them whenever appropriate. Okay, so let's start with a little bit of a history of open source and mobile communication protocols. You have to remember that we started about 16 years after the proprietary implementations. So the GSM network that we are running here at the event, or that we started to run 7 years ago, started 16 years after GSM networks were run first in the public in Europe, so at public operators. So we're really, really late. And if you want to compare the status of open source mobile communications with open source operating system, then I would say we are about where Linux was in 94 or 95. So very far from today, for those of you who are old enough to remember these days. So I would say capable but not taken seriously is sort of the general status. The developer community working on these projects is still very small. There's limited adoption in the market and the users, often in niche applications. But nevertheless, it is functional. So if we look a little bit at the timeline, 2008, we had the talk about running your own GSM network with a huge Siemens base station weighing, I think, 28 kilograms. Did my microphone? No, it works, sorry. Weighing 28 kilograms and bulky old equipment, not using TCP/IP, but using E1 lines and so on. Over the years, we added more and more BTS model vendors. That basically means we can use Ericsson and Nokia and other equipment to actually run these GSM networks today. People have been working on GPRS support in a couple of sub-projects called Osmo SGSN, OpenGGSN, also the Osmo PCU project. So we've been growing the stack downwards, also basically implementing the software inside such a BTS, which we call Osmo BTS. There are some production deployments, all spellings my mistake, by the way, as obviously. So production deployments in niche applications such as maritime markets. So if today you're on a ferry or on a cruise ship and you use GSM services, the probability that you're using OpenBSC and associated projects in the background is very strong. There are hundreds of vessels using our software today. Now then Then we moved on the telephone side. So we thought, well, network side GSM is one thing, but let's do the phone as well. That was Osmocom BB, started in 2010. We did improvements over the years, more and more completed the stack, but it's really all only old GSM GPRS technology until very recently. So in 2015, 15 years again after the first commercial deployment of GPRS in a public network, we start to have an open source implementation of Edge. And that has just started like 2 or 3 months ago. So again, 15, 16 years late compared to what happens in the proprietary world. Okay, but this talk is not about Edge, which is 2.75G, if you want to speak in generation numbers. Today we're talking about 3G and 3.5G. And there's a bit of ambivalence with that subject because, well, today if you talk to people in the industry, they will say, who cares about 3G, you know, it's dead anyway. We have already today at the point where we have peak 3G. So in the next few years, the number of subscribers and the number of networks offering 3G services is no longer growing. It's basically stagnating and will turn downwards in the near future. So LTE 4G networks is basically what everyone is hot about. The other reason not to look at 3G is that it's mind-bogglingly complex. It's not a single telephony system. It's actually a toolbox to build arbitrary telephony systems. And if you really wanted to start implementing it from scratch, including all the lower layers, including the PHY, including the layer 2 and so on, I think it would be a waste of a lot of time, actually. So we do what we did with the GSM networks back then. We use proprietary base station hardware, and we implement the higher level protocols. And then, if needed, and if there's interest and contributions and so on, we drive open source further down the stack and also into the actual cells. So one term that's going to be used here in this context is femtocells. Quite some number of people may have heard about femtocells before. In technical terms, it's a base station, which is called Node B in the UMTS language world, and a radio network controller, which is the BSC, the base station controller in UMTS, in one box. And using such femtocells or similar hardware, it's much easier to interface than if you would use a regular base station. So that basically is sort of a path that we think is doable without spending many years of implementing obscure and complex transport channels and bundles and mappings and whatnot. There's been a couple of talks about doing creative stuff with femtocells. There have been talks by Kevin, Nico, and Ravi Shankar in 2010, 2011 about security. There's been a recent presentation this year at Black Hat in the United States called Adventures in Femtoland. Those talks focus on basically, well, the security of the femtocell itself, breaking into such a cell, rooting it, owning it, doing creative things, and then from there, for example, attacking the mobile operator or attacking the privacy of subscribers by using such a femtocell as a man-in-the-middle platform, for example. But to my knowledge, nobody has been talking about free software or open source software to run a network with such femtocells or similar equipment. So if we look at the UMTS architecture, like you find it in a textbook or like in this particular slide or drawing from Kevin, you will find several network elements all over the network, so lots of different elements with lots of different acronyms. We have a mobile equipment, which is the telephone. We have a radio interface called the UU interface. We have actual base stations called Node B. And we have a base station controller that's called the radio network controller, the RNC. And then here we have on this boundary, we have IUCS and IUPS interfaces that interface the actual base stations with, or sorry, the base station controllers with the core of the network, which is the mobile switching center, the media gateway, the serving GPRS support node, and other elements here. And this is actually the interface line which we have been implementing in recent months at the boundary between the access network, or the radio access network, and the core network on the other side of the slide. So You could just get a node B and implement the protocol IUB. This is what we did with GSM before. We basically started here. We only got the actual BTS or node B, and we implemented that protocol. However, this protocol in UMTS is extremely complex and fairly low down the stack. Just to give you an idea, every single voice codec frame from a voice call that you receive has 3 different classes of bits, and each class of bits gets put into different UDP messages, and then you get basically 3 flows of UDP messages, and you need to synchronize and intermingle and re-interleave those bits in order to get to a speech codec frame. So it's, and I'm not even talking about the signaling plane. So the lower you get in UMTS, the more complex it gets. Let's try to avoid that. And that's the kind of complexity that I like to avoid. This is from the official spec about the UMTS spectrum. It's an extremely obvious and self-explanatory slide, so I leave it at this and say, yeah, that's not what we want to do. So how can I say, even though we don't like it, we just use proprietary blobs to implement that. Now, the protocol stacking on those interfaces that we actually want to implement is what I'm going to look at the next couple of slides. The IU interface, and by the name, IU has no specific meaning. It's just the IU interface. You could say the A, the B, the C, the Z interface. It's the IU interface. It's split in CS and PS, the circuit switched and packet switched. Circuit switched means telephony services, and packet switched means data services. We're going to look at the protocol stacking of those interfaces in the next couple of slides. Originally, remember, basically maybe a good time to go back in history, in sort of history of mobile communications, which should be taught at every school, I think, including archaeology of protocols, which... No, honestly, you need to do protocol archaeology if you want to implement certain interfaces today. So on my blog, you can find some posts about a couple of years ago where I had to basically write a parser for Microsoft Word for DOS text files to automatically extract snippets of ASN1 syntax for map version 1, which is still used today. So sometimes you really need to do archaeology. So anyway, not for this, but when UMTS was specified, this is the late 90s. This is when the first .com bubble basically got big. This is when billions and billions of euros or dollars or whatever unit of currency was poured into the development of the universal telephony mobile system, universal mobile telephony system, the UMTS. Which should basically be the grand unifying theory of mobile communications. It was built on top of ATM, of course, because ATM was the most shiny and brightest technology in the late 90s that all the universities were researching. So if you look at the classic protocol stacking and you look at the individual interfaces, the UU is the radio interface, IUB is between the node B and the RNC. But this is the IUPS is actually what we want to implement. So basically, the left side of this slide is what is implemented in the proprietary base stations or femtocells that we are using, and the right-hand side of that slide is what we are implementing. So we need to implement the protocol stackings here. As you can see, the protocol stack is deep and has many acronyms. To make things more complicated, the femtocells that you can find on the market are slightly different from the real normal 3G architecture. So if you try to compare this slide with that slide, you will find some differences here. The difference is that they introduce a security gateway, which is basically just ITU and 3GPP language for an IPsec gateway. You have a home node B gateway that doesn't really do anything useful, rather than putting messages from one protocol stack on the left to another protocol stack on the right, with the underlying protocols doing exactly the same thing but being differently encoded. And this is what you can see here, basically, the home node B gateway, which is part of the software that we implemented. You can see basically, you have RANAP. This is the protocol that really is sort of what we're interested in, the radio access network application part. And RANAP, in order to implement that, there's several other protocols underneath. And on the femtocell, which is called H node B, the home node B, because well, femtocell is a marketing term, and specs can never use marketing terms, so they have technical terms. So the femtocell basically encapsulates RANAP into RUA, the RANAP user, what was it? Sorry, adaptation, yes, the RANAP user adaptation. So the radio access network application part, user adaptation, on top of the SCTP, the streaming control transfer protocol, which some may know is a protocol that's on the same layer as TCP or UDP, but has different properties. This RUA is implemented in the home node B gateway, where it is replaced by M3UA and SCCP. And then basically the same RANAP message gets passed from left to right. So it's really, you could think of it like an IPv6 to IPv4 proxy. If that's more an area that you're more familiar with. Okay, so yeah, as I said, there's some differences between an actual regular old-fashioned UMTS base station, like your public operator would use it, and the home node B or femtocell that we like to use in this project, at least initially. And as I said, the main difference is that the RNC, the radio network controller, is built in, so a lot of the lower layer protocols are terminated, and we don't need to worry about that. If we look at the protocol stacking again, there is a lot of protocol layers here. You can see the MAC layer, the RLC layer, the RRC layer, and all the physical stuff underneath is all basically already implemented because it's part of the femtocell in this case. So the protocol stacking now looks a little bit like this. We have the home node B, and the home node B gateway, and then our core network elements already. So the SGSN and the GGSN, if you've looked at GSM in the past or GPRS, even the software that exists today and for many years in the Osmocom project, we have implementations of those. What we're missing is the home node B gateway, and is all the fancy new protocols here and some modifications. So, well, what do we need to do to actually implement? This IUH protocol. As I said, there's the different protocol layers. There's RUA, there is the RANAP protocol, and the HNBAP protocol. Let's look at those protocols, what they do, and how can we implement them. I'm skipping a few slides in the middle because it's illustrative if somebody wants to check the slides later, but it would go into too much detail at this point. So the RANAP user adaptation layer, given the spec number above there, so if you look for that online, you can find the actual spec, is a very simple connection-oriented layer that provides you the notion of a connection over a datagram transport layer underneath. It has very, very few operations and message types, including connect, which, well, surprisingly sets up a new connection. Direct transfer, which transfers data inside a connection, disconnect to terminate a connection, and connectionless transfer to transfer data outside of a connection. And of course, an error indication in case something goes wrong. So we can have multiple connections in parallel over a signaling link, and they are distinguished by a 24-bit context ID to differentiate those multiple parallel connections. Think of it like a port number. In the case of UDP or whatever else you might want to compare it to. So this, if you look at this and you read the spec like, oh, it's nothing. It's like, you implement like 5-6 message types and that's it. Well, there's a bit more details to that, but we'll get back later to this. The home node B home node B application part, the HNBAP protocol, has a couple of more transactions which basically serve for the registration of the cell to the network, the registration of user equipment, UE, that's your mobile phone, and some additional messages. So HNB is the home node B registration. We have registration, request, accept, reject, deregistration. We have the same for mobile phones. We have some more detailed transactions that I'm going to skip, but also it's really very simple. Conceptually, it's not very complex. You don't have like massive state machines or anything like that. Very few, very limited messages. Then we look at RAN app. That's the radio access network application part. This is where your actual signaling messages from the phone are tunneled through. So if your phone registers to the network, you may have heard the term location update, where the phone basically registers to the network or updates its location with the network. That's the first message you would see encapsulated inside RAN app and transported to the core network element. Also things like PDP context activation, if you activate a data connection to a certain APN over cellular protocols, all this is encapsulated in the RAN app layer. Also, the number of messages that we actually need is extremely limited. Again, it's a very short list. It's not like hundreds of messages. But the messages themselves can be quite complex, with nesting levels up to 12, 14 layers deep, but we'll see that later on. So we have a couple of transactions. Reset, well, I don't need to explain, it's a reset. Initial UE message means a new phone has connected and it has sent us the first message that this phone has transmitted. That's why it's initial message. Direct transfer is all the follow-up transfer. IU release means, well, we're releasing a connection. Some commands to configure the security, the ciphering, the encryption, a paging command by which the network can initiate a transaction to the phone, and RAB assignment. RAB is the radio access bearer, which is basically an abstract notion of a bearer able to transport communication. I mean, if you come from classic telephony, the bearer was, well, an analog voice channel. If you go to ISDN, the bearer is, well, it's a 64 kilobit synchronous channel where you have A-law or U-law inside and voice data, or you have some HDLC or X75 or whatever data inside. In GSM, well, the bearer is typically voice bearers with different voice codecs. The same is in UMTS. Basically you can configure those bearers in UMTS because that's a very universal and flexible part of the system. Now, one of the protocols we have seen in the stack, I'm just going back a couple of slides to reiterate that, is the SCCP, which is introduced here, the signaling connection control part, if I remember correctly. It's a protocol that's used a lot in core networks of mobile operators. So if you look at roaming interfaces, at classic SS7 interfaces, think of the SS7 security talks and so on we've had here at CCC events a lot of the times. This is a protocol that's very often used in a lot of different parts of telecom, but the problem is everywhere except this particular point in UMTS and GSM, it is used only in connection-less mode, and this is the only point where it uses connection-oriented SCCP. And therefore, none of the existing free software implementations implement it. You can look to Yate, you can look to the libosmo SCCP, the library that we have in the Osmocom project. You can look at the Mobisense Java stack for these protocols. You can look at the Osmo SCCP Erlang code. Basically, no implementation exists, so we also had to implement that part, at least to the point, to those features that are required. Well, once we have implemented all these protocols, RUA, SCCP, the RAN app, the HNBAP, then we need to somehow interface those protocols with the existing network elements that we have for GSM. And there are sort of several challenges in this area. In the what people know as the OpenBSC project, actually the program that most people use is called Osmo NITB, the network in the box, which is called network in the box because it implements all the network elements that you need in one box or in one program. Unfortunately, we need to separate those individual pieces, which are all in one blob, in order to interface at the point where we want to interface. So there's a separation of the MSC part and the BSC part needs to be done inside the network in the box. We need the UMTS authentication and key agreement support. We need well, the different protocols that I just mentioned and link them in. on the SGSN side, for the data services, we need to introduce some abstraction to basically differentiate the packet data connections coming from GPRS networks and those coming from the new 3G networks or base stations that we are supporting. But that's all manageable. Now, the question is, do we really want to go for the full stack as it has been described, or can we take some shortcuts? Do we really need to implement the full SCCP, for example? Do we need to implement M3UA, which is another protocol layer in there? Can we basically simplify that? The initial idea was, if we go back to that slide, to reduce the complexity. I already mentioned this home node B gateway, which basically passes RANAP from left to right and just changes the underlying encapsulation. Why don't we just continue using RUA up into the SGSN and thereby avoid having to do SCCP and M3UA? Avoid having to implement more protocols without having any functional gain. I mean, it would just work the same way if we take RUA and we take it all the way into the SGSN. So there's been some thinking along those lines, but the idea was to go sort of in a compromise. So what we're using here is yet another protocol called SUA, the SCCP user adaptation. And that replaces those two layers and keeps things a little bit simpler from the implementation side. Okay, now we have all these different protocol layers and the integration into the core network elements. Now the fun starts. We have a plan. We know what needs to be done. And now we actually need to do it. So the theory was easy. Read a couple of specs, find out, 6, 7 messages, not too many transactions, no complex state machines. Okay, now a lot of the more modern telecom protocols use ASN1 syntax. It's an abstract syntax notation for defining data structures or procedures to be communicated. And then you can use code generation tools to generate code in your favorite language from this syntax, doing all the marshalling and demarshalling of the messages. That's at least what's the idea. This is very different from what we used to do in the GSM world, because GSM was specified in the late 1980s. ASN1 didn't exist to my knowledge back then, or at least they didn't know about it, or they thought it was not something that you could do in a mobile phone at that time. Think about 8-bit microcontrollers and whatnot, what they were using these days. So the GSM messages, basically you look at the spec and you see, oh, there's 1 byte this, then there's a 2-byte length field, and then there's that, and you need to implement that basically in your code based on the textual representation. Now, for UMTS, almost all the protocols, and particularly these that we are looking here, are specified in abstract syntax notation, which, well, on the one hand side, you would say, oh, yes, great. Now we don't need to write all this message encoding and decoding code, and then we end up interpreting the spec different, and we have sort of incompatible messages and whatnot. That's true to some extent. Okay, now what you need to know about ASN1 is there are different encoding rules that define how the abstract syntax notation gets converted into a concrete binary representation. There is basic encoding rules, BER. There is all kinds of encoding rules. There's even JSON encoding rules these days. There's also XML encoding rules. But what's used here in these specs is called aligned packed encoding rules. This is a particular encoding rule that was not or is not supported by any of the ASN1 compilers that exist in open source that generate C code. So we first had to teach the ASN1 compiler this encoding rule. And the second big problem is the ASN1 syntax used in those protocol specs uses a construct called information object classes, which is sort of, well, an interesting way how to express or how to have a different notation on how to construct those messages and how to construct operations that have like an initiating request, a successful response, a successful error outcome, or something like that. And you can express that in a really nice way, but then you need a compiler and a code generator that can parse that. And that's really difficult in the free software world within some constraints. I'll get into the details. Now, the next thing is that the way how they use ASN1 in these protocol specs, ASN1 being the abstract syntax notation is not abstract enough. They need to have another abstraction layer. So they use ASN1 to describe containers for information elements, containers for messages, containers for lists of information elements, and containers for pairs of information elements. It's very important. You cannot just have a list of two. No, you need to have a pair that says, well, this is a pair of two information elements. Not sure why, but somebody probably had his reasons for doing so. Now, the point is basically you use the ASN1 syntax and you generate some code for encoding or decoding, and then you're not really done at that point. Because then you basically, oh, this is a list of containers, and then you need to look into each of the containers and then call the decoder again for each of the elements in the list. And then in there might be another level of containers, and you unpack it again. So it's a little bit like Matryoshka or these dolls nested in each other, or somebody sends you a large packet and so on. Well, so to illustrate that, if you've ever seen ASN1, this is a relatively simple example describing authentication tuples or triplets or quintuples. Basically the authentication data that's used for authenticating subscribers in networks. This is what is used also in GSM. It's relatively simple. So it basically tells you, well, there's an authentication set list which contains of a choice of either a triplet or a quintuplet list. Each of those lists either have a length from 1 to 5, and then you have basically a sequence which is sort of a struct or a record of the below items in those lists. That is how ASN should look like and how it normally looks like. Now, in RANAP and these protocols, they first, as I said, they define these containers. They say, well, oh, we have, so it reminds me a bit of some mathematicians. It's like, oh, well, we define, we have this, and then we have that, and therefore we can construct such a new structure and whatnot. So basically, they define first a container for protocol information elements, protocol IEs, and then the protocol IE is the actual information element. Each element has an ID, it has a criticality. The criticality tells you whether if you do not understand such an information element, should you ignore it, should you reject it? Should you ignore it but report to the sender that you did not understand it, despite proceeding with your operation? And then the actual value. So, and the value is an any type, which means there is another ASN1 syntax in that value that you then need to parse. So you need to do these two steps in the code. You first unwrap the containers, and then you decode what is inside the containers. So working with ASN1 really is not as simple and as straightforward and as automatic as it should be. And you end up with messages looking like this in Wireshark. So believe it or not, the content, the useful content of this entire message is 4 bytes here, the Z0. The 4 bytes starting from Z0, and those people who have seen an IP address, an IPv4 address in a 192, 168 address range will recognize those bytes here at the end. So the Z0 is 192 and so on. And in order to communicate, this message actually, this is a message that tells us to which IP address something has been bound to. In this case, it's the GTP connection for communicating packet data. And you see all these abstractions and encapsulations and the nested tree. So it starts with, well, okay, this is an outcome. It is an outcome to the radio access bearer assignment. If you do not understand it, please reject it. We have an assignment response. It contains of a list of one item of protocol information elements. This one item is a setup or modified list, which again has a criticality of ignore if you don't understand it. Here it says, if you don't understand it, just ignore it. Don't report an error. It's quite interesting because you have a message that only contains one element, and it says, well, you should reject the message if you don't understand it, but then the information element says, oh, if you don't understand it, please ignore it. Okay. Then inside the setup or modified list, we have one item, which is a protocol ID container, IE container with one item, which has an item which is the setup of modified item, which is a radio access bearer modified item, which contains a radio access bearer setup or modified item with a radio access bearer ID of 1 and a transport layer address of this. And in case you're wondering why the IP address has such binary crap in front, it is because it's too difficult to express in ASN1 that this is an IP address. You could not just define a type for an IP address. That would be too simple. No, you need to refer from this specification to another specification, another 3G specification, which then refers to ITU-TX 213, which tells you how you can encode any possible transport layer address in any possible network protocol on the planet by using a hierarchical structure like OUI IDs or something like that. And 35 means it's an IETF allocated address. 0001 means it's an IPv4 address. And then you actually have the payload. And you can see Wireshark is too stupid to decode such brilliance. Yeah, so then it's hard to find example traces. You want to implement the protocol and you want to find some example traces. This is a mail. I was looking for this year in 2015. I was Googling for IUH protocol traces. And what did I find? My own email from 2009 where I was asking for protocol traces, but nobody ever responded. So the situation is better today. You can actually find, I think, 2 or 3 public PCAP files containing each maybe a handful of messages on those interfaces. It's odd, you know. These are protocols that are specified publicly. They're used in production. Billions of users are using these networks, but nobody even has an example protocol trace of those protocols. Okay, now we have a couple of protocol traces. We understand the nesting level is deep. We are happy that Wireshark decodes at least most of it, which, by the way, we have to thank one particular Ericsson employee who is contributing those dissectors to Wireshark. Yeah, so then we need to basically set up a tool chain to generate code for from these ASN1 syntaxes. So there is an ASN1C compiler from Lev Volkin. It's good for a lot of things, and I'm very happy it exists, but it lacks many, if not most, of the features that you need in the telecom world. That's sort of unfortunate. There's no information object classes. There's no aligned PER support. There's no support for prefixing the type names, because we have 3 different protocols. We want to use them from one program. We need to prefix the type names, because, of course, each of those 3 protocols has a type called protocol information element container. But, of course, it's not the same protocol information element container. There's an each of the protocols has its own containers. Yeah, so we had to add these pieces to the ASN1C, at least in a minimal way, in order to use it. And unfortunately, I don't know anyone, and I'm certainly no one who understands something about compiler theory, so it's a little bit challenging. Now, alternatives to ASN1C, well, the most complete toolkit you can find for working with ASN1 exists in the Erlang OTP system. Well, I used this in the past for a lot of Osmocom projects, but well, the fact is the C projects, there are other developers and people that contribute, and the Erlang projects, there is nobody that contributes except from me. So I thought, well, okay, it's very nice to work with ASN1 in Erlang, but then if nobody contributes, I'd rather go the difficult C way and then have contributors in the project. Also, of course, in the Osmocom project, we're mostly low-level C guys, and people are very, how can I say, wary of virtual machines and the at least perceived bloat they introduce. The third alternative is to use a proprietary ASN1 compiler, and in my day job, I actually use such tools, but well, in the first side, you think, well, okay, it's a code compiler. It compiles code. And the copyright law says, well, code that was generated by a machine is not copyrightable, because the act of automatically compiling code from one form into another form does not create a copyrightable work as itself. So basically, you can take a proprietary ASN1 compiler, compile C code, and then use the resulting C code in an open source project without having any problems with the license of the ASN1 compiler. That's true. However, all those compilers I know, and I think I know all of them, they have a runtime library, and that you only either get in as a binary library, or you get it in source code that's not available under a free software compatible license. So, well, no option to do that. So we have to stick with ASN1C, which, as I said, I don't want to complain about it. It's a great project. It just doesn't do all the things that we need, but then it was not written for us. So, of course, it doesn't do everything we need. So, okay, luckily, a research group at Eurecom, the European Communications Research Organization, has developed a patch for adding aligned PER support to ASN1C. Unfortunately, it was against an old version because, well, they probably don't want to submit this mainline and they don't care about porting it and rebasing it. I did that. It probably still needs some cleanup before it can be submitted, but my goal is to have this to have this included in ASN1C. Also, we found quite a number of bugs still in the code, so it's in the process of being improved. Now, information object classes are hard, at least for me. Basically, we skipped that. I manually edit the ASN1 syntax for not using information object classes anymore, so I'm rewriting the ASN1 that's supposed to be there to guarantee that the encoding is so it circumvents sort of the purpose. The idea is you take the ASN1 from the spec, you use it, you don't modify it. But I'm modifying it because, well, the tools we have are not good for what we want to do. Type prefixing is done. Now we have the information element containers. Eurecom has another idea about this. They have a long Perl script. I recommend you not to look at it. It consists of a never-ending sequence of regular expressions, basically grabbing out certain parts of the ASN1 syntax without really formally parsing it or lexing it or tokenizing it. And then based on those regular expressions, generating C code that then you can use with ASN1C and link against it. And surprisingly, it works, surprisingly good, actually. We had to teach it all the things that we needed in addition to that, but really it works surprisingly. Now, putting the things together, copy and paste the ASN1 syntax from the 3gpp.doc files, because 3GPP specs are published as PDF files and as Word documents, and you don't get the actual syntax as a text file. You have to copy and paste from each page, make sure you don't get intermixed like headlines or something like that. Then you use the hacked up patched ASN1C to generate C code. You have to modify it to make a shared library of the runtime for the ASN1 compiler, because we have, again, 3 syntaxes that we want to mix, and that doesn't really work with how ASN1C works. We use ASN1 struct to remove this, what I call the obfuscation layer, these containers. We write some code to dispatch the messages, and then finally we see some messages. So we have those HNB register, initial UE message, and all these things. This is what you can now get from osmo.ioh.git. It's a Git repository on the Osmocom server, which contains all this code. It takes a long time to compile, because ASN1C generates 1 C file and 1 header file for each type. And they have lots of types in those specs. So you end up with like 300, 400 C files and header files compiled into a 5 megabyte binary. And then finally, you want to get 4 bytes in a message. Well, where do we go from here? We have a couple of other things to do. One interesting question is, and I'm going to do a demo in a few minutes, is what kind of hardware can we use? Well, the hardware that I currently use for this development is undisclosed manufacturer, very expensive. It's not actually a femtocell, it's a real cell. Costs several thousand euros, not really suitable for hackers. However, many consumer-grade femtocells have also this IUH protocol with the same stacking. The problem is they're locked down in a way that they have certificates and connect over IPsec to the operator network and so on. So if somebody can break this IPsec layer and insert his own certificate or disable the IPsec altogether, then you can talk IUH to the Osmo IUH, and then you can use that hardware. This is something that a couple of people have looked at, and hopefully in the near future we will have 1 or 2 femtocells that people can use inexpensively in order to use the software. At the moment, as I said, unfortunately, it's not possible. So, well, as a summary, before I go into the demo of demonstrating it and you having basically a look in the marvelous depth of the Wireshark decodes, IUH is conceptually very easy to understand. The lack of good ASN1 tools is the biggest problem in the free software world. you need to overcome these containers, and in the end, you spend 90% of your time in improving the tooling, fixing the tooling, and working around these layers of abstraction rather than doing the actual functionality. We have started the work on the core network components, the integration. I was hoping that I could do a full demo with a call or a full demo with actually having a data connection over the setup that I have here, over the test setup. I'm almost there. The signaling, everything gets established, the authentication works, but then somehow the data, the actual IP data doesn't want to come through. And that is under investigation, but I'm sure it will be available rather soon. Okay, so now before we go for Q&A, let me just do a quick demo and let me show you how this looks at the moment. Okay, this is still a protocol trace basically that was running in the past. I'm just going to leave this here on the left-hand side. I'm going to leave on the right-hand side. So what we can see is basically on the left-hand side, we have the RUA encapsulated messages. This is basically the IUH interface between the home node B and the home node B gateway. Then we have the Osmo IUH home node B gateway, invisible in between here. That's the program running in the background. And then the other side is this protocol stacking here, where we see we have the SUA, this SCCP user adaption, rather than the RUA on the left-hand side. The RANAP messages are the same on left and right. It's basically just converting. What I'm going to start in the background is basically, this is the wrong window. I thought I had prepared everything just, yeah, exactly. Good, that's the one part. That's the other part, yeah. So I'm going to start I know the font is too small, you don't need to read that. I'm just going to tell you I can make it larger, but then we won't see really a lot. What's this? Why is it not? Cannot listen on MS socket. Now that's the demo effect. Why on earth is it not binding? What a pity. Okay, that's embarrassing. Then you get a larger font size. And then let's have a quick look. I'll try it very quickly. So I'm trying this. It cannot bind to the sockets. Probably my IP address has disappeared on the laptop while I've been talking here, and now it wants to bind to an address that doesn't exist anymore. And that seems exactly what has happened. No. Don't shout your sudo. It will not like you. I can tell you. Yeah. Okay, now this should do the trick. I'm starting this in Valgrind because I'm still debugging. Yeah, now it's actually running. Okay, now we do the same on the other side. We go for a huge font size. And I'm starting the HNB gateway. We see a yellow line that a connection has been established. So now we are waiting for the initial message from the home node B to arrive. We should see it here at the bottom of this trace. We should see a couple of reset requests. Basically, the home node B, the node B here, is trying to reconnect all the time to its home node B gateway. Of course, there's some backoff included, and given that it was not connected for the past 40 minutes or so, it will take some time to reconnect to the SGSN, and then I can have the phone that I have here registered.
And is there somebody somewhere at the mic? Mic 2, please.
So if 3G is so annoying, why not skip it and go directly to LTE?
Well, there's a couple of reasons for that. First of all, some people really need it in terms of there's an actual demand for 3G small networks or 3G cells in applications where it's used. The second reason is it's a relatively limited incremental step because the layer 3 protocols of GSM and UMTS are the same. And that's why basically we can reuse the call control and the mobility management, all those parts from GSM and reuse them with 3G. I'm not saying we shouldn't do the same with LTE as well, but there are actually quite a number of projects already involved in that area. And LTE, well, to be frank, it's so much IP, it's not really telecom anymore. I'm always interested in the more obscure things that people are not really looking so much at. IP, I found IP boring when I stopped working on NetFilter in 2004. So I was like, IP, well, everyone knows about IP. That's, we need something more interesting. Okay.
Microphone 1, please.
So you say that you have a lot of trouble parsing AS1, but if it's always the same containers, can't you simply have a static dump of the binary crap before and after that stuff and ignore the whole parsing part?
You probably could, but then, how can I say, my code aesthetics demand better behavior from code I write than just doing something like that. So yes, you could probably, but I'd rather have a more clean way of doing that.
And continue on microphone 1.
You said that UMTS or 3G is a toolbox for creating arbitrary telephony systems, while my knowledge tells me that GSM is a much more rigid standard. But if you could please elaborate on that concept of arbitrary networks.
Okay. Well, I could illustrate it very much with a certain protocol trace. UMTS, basically, when UMTS was specified, they didn't know where the journey was going to. Basically, it was not clear that the internet would be the thing that we know as of today. They didn't know that smartphones would exist. They didn't know that IP data services are the type of data services that people are interested in. Rather, they were thinking of in generic terms. So it could have been that we needed all x25 over UMTS. It could be that people wanted to do ATM over UMTS. It was not clear that circuit switched services would basically go downhill like they did meanwhile with voice over IP telephony and so on. It was not clear that modem calls or actual video calls that exist in UMTS would not be the future. So it was very unclear, and they tried to define something that's as flexible as possible to do anything that you could imagine. And if you look at the way how the layers are structured and the fact that you have transport channels and transport channel bundles and radio access bearers and so on, basically the structure, even only to transmit voice again, you have to set up with AMR for all the codecs. You need to configure in the physical layer, I think, for the 3 different bit classes, 10 different combinations. So you end up with something like 30 parameters or 30 sets of parameters that you need to communicate to the lower layers only to configure it for establishing a voice channel. And then the transport channels where the bits are included, the payload, like how many bits fit into one frame, doesn't match with your codec bitrate because they didn't know what codecs they would use. So it's all arbitrary and with padding and universal. So it's not like GSM. GSM is very simple and straightforward.
Okay, we have 5 minutes left, so we will have 2 quick questions from the internet because everybody on the stream, you can actually ask questions on the chat, please.
Okay, thanks. We have 2 questions, as you said. The first one is if there would be interest in implementing, the whole stack in a safer non-VM-based language if the tooling was good enough.
Well, I mean, it depends on, I don't want to find language wars here. I would have been tempted to do things in Erlang, but then as that, the question is who else would have been tempted? I don't think, I mean, the point is what we're trying to do now is to basically use most of what we already have with the least additional effort. And I don't think anyone will want to start from scratch all over again. But if they do so, I would be happy to see a clean implementation, but I'm not so sure that will happen.
Okay, thanks. And the second question is, why don't we just start over from a clean slate with hardware and software and do basically 100% nerd and hacker-driven mobile networks?
Sorry, 100%?
Nerd/hacker-driven networks.
Well, I mean, the point of implementing all those specs is you want to use the existing devices out there. You want to use the existing billions of mobile phones that exist on the planet. And if you want to talk to them, then you need to implement those protocols and those systems that they implement. If you want to start from something else and do things from scratch, well, yes, you can do that. But then keep in mind that you will have very bulky end-user equipment with large clusters of FPGAs and DSPs, draining batteries, having fans inside, because you will not be able to implement your system in the same level of energy efficiency and the same level of ASICs and optimized silicon processors and so on, like is the case for the billions of existing devices.
Okay. Thank you, Harald Welte.
Yeah, thank you.